Good morning to all. We continue with the CDC Solution Designs for the multi-bit across the asynchronous clock domain. In this video, we are going to see the FIFO for the multi-bit or vector data across the asynchronous clock domain. So please do check my EDA tutorials for the VCS and the design vision. Let's start with this FIFO. So dual port memory is the heart of this FIFO arrangement, where one side is nothing but our writing arrangement, like we check whether the FIFO or memory is full or not using the W full signal, and if it is not, we can write using the this W increment pulse. Okay, and the clock we are using for the write is a W clock, and for the reading we are using the R clock. So there is a separate reset arrangement for this arrangement, and it is sourced from the Sunburst document. Okay, actually, so basically what happened, if the FIFO is not full, the host can write the things into this memory up to the size of the FIFO, and if there is no empty signal is there, then the slave or something like that can read the data from this FIFO. Okay, and the pointer to check whether this is up to that empty or full or something like that, we cross check both the pointers, write pointer and the read pointer, at both ends, at the writing end as well as the reading end. So to transact this address or pointer value, basically we are using the binary to gray arrangement here as well as here. So the addresses going to this dual port RAM is from this W address, and the reading address coming from the reading side R address. Okay, and obvious there will be the double flop synchronizer there, so it is called sync R2W and sync W2R. Okay, so we will see in this code what kind of code is written for this arrangement. Obvious there is a one FIFO which is our dual port RAM, then these two flop synchronizers. Obviously it is for the multi-bit, and there should be some conversion, binary to gray and gray to binary for the checking purpose. So while this is a write clock, read clock, increment, write increment, read increment, and this is a W data. So W data come in sequential manner with respect to the W increment, and it will continuously fill the FIFO. Okay, and we are taking the FIFO length is almost 16 here, and the increment clock is used for the read the data from the FIFO. Okay, so initially it is looking to be the empty. Once the W data or writing process is going on, it will automatically goes to the R empty with respect to the. So once the complete 16 data get filled into this FIFO, the W full is acknowledged. Okay, and we can pull the data from the FIFO like 2481, 2481, 09 one by one with respect to R increment C. So at last what happened, we consecutively read all the data up to the 16th, then RMT will go high for the further process Basically it is in test bench, we are not consecutively write the data here. So up to the 16 we write, then we stop, and then gradually we are reading the data. Okay, so if multitasking is there, then we can have the continuous data write up and read up from this FIFO. But for check purpose I just do it. It is a RTL based simulation, so we cannot see any glitches on the R data, but after the post synthesis I think we get some glitches at the receiver side. So the code that we are referring here is listed as a path in the all file list. This is our top, this is our test bench, this is our dual port memory, read pointer empty, sync R2 W, W to R, and the write pointer for the indication of the full. So this is our reference 90 nanometer. Those who are not already seen our videos, so these are the folder details we are keeping. This is for the all the resources. We are keep the Makefile here for the simulation based on the RTL and synth. DC90 has a tickle file for the synthesis using the 90 nanometer work folder from where we are running the design vision. Under the result folders there is a DC90 nano which has the synthesis result, which is our gate netlist results that we are using for the simulation while for the synth mode. And obviously there is a file list called allfiles.txt, that is this one. Okay, and for the design vision simulation we refer 90 nanometer library. All the codes are located at the another code folder. Okay, and the file list is in allfiles.txt. The simple command is there, dc shell -f tickle file, then whatever the top, basically we are using the FIFO1 as a top module name. This is a VCS RTL test bench setup for the RTL. So obviously the mode is RTL. For the synthesis the mode is going to be the synth. Okay, so we will check one by one all the codes and try to get the synthesis process and check the VCS simulation on the post synthesis. Okay, so before that we just overlook the simulation using the ActiveHDL here. This is main module, this is test bench. So as we see there, it is the same waveform that I dragged from this. Okay, so there is no much to explain here. Back to the terminal so that we can check all the codes first. So cd code, so we check the first FIFO 1 dot. So we are keeping the bus size 8 bit and the address size is 4 bit. So obviously there is a 16 locations in the FIFO. This is our top where all the models, that is saying R2 W, W to R, FIFO mems, and the read pointer, write pointer, and one additional I use one flops for the R data to minimize the glitches, but still it is not minimizing that. Anyway, we'll see in this R data 2. Okay, so next we go to the test bench. So this is simple test bench where we create 2 clocks and 2 initial blocks for the one for the looping for the write and read. Okay, So there is no much to explain here. You can refer the Sunburst document where you can find this kind of code. I took the as similar to possible to that Sunburst document. Might be the reset is for the asynchronous, but for the simulation we took as it. Okay. Otherwise we have to use the synchronous reset there. Anyway, for the read pointer, this is a code for the read pointer empty. Okay. Obviously there will be some conversion binary to gray. Okay, and there is a check for the whether that pointer is 0 or not, or equivalent to the gray value for the generation of the read empty. Okay. Similarly, there is a write pointer or write full. So this is the code for the generation of W full. Okay. Obviously there is a use of the asynchronous reset here, but for the reference I took it as it is from the Sunburst. So there is one more code, FIFO mem, where the dual port memory is instantiated. So actually for the RTL I just use the reg option for to create the memory, but if you have the vendor based ROM module with you, you can use this def for the vendor based RAM. Okay, so you have to change the name of that vendor RAM here. Okay. Accordingly you have to add the library according to requirement of the vendor based RAM. Okay, but for the RTL purpose we are using this simple reg, which is obviously have the implication of the DFF while synthesis process in the main RTL. So that should be keep in mind. Okay. So I hope there is no much say about this. Okay, we can check R2W. This is just pointers, double flop pointers, and there will be some similar version for the so this is same we as discussed. This is just a double flops kind of thing at the receiver side or transmitter side as well for the pointer exchange. So let's say how we can synthesize this code. So we go back to the DC 19 nanometer where the tickle file is there. So RTL tickle, this is a tickle that we generally refer for all our earlier designs. Okay, so for the reference I just scroll down slow by slow. Here we are using the main clock as a W clock. Okay. So we will see later on what CDC what errors warnings will be there if in CDC tool, that is Spyglass CDC. For sake of simplicity we are just took as a W clock as a main clock here. Otherwise there are a lot of problems coming with this. So our result reside in under this result DC9090 report. Obviously there is some that what we can say that gate net list. Yes, gate net list. As a gate net list, we have the top level module append with this and the .v. This is our gate net list, which is reside in our results under DC90. Okay, we'll see that also. So we back to the one more file we need to check, that is our all file list .txt. So just okay, this is our file list as we refer earlier one. What is that? Okay, so the command for the design vision, we generally start with from the work folder. So the command will be the dc underscore shell -f tickle file name, then my top equal to FIFO1. Okay, hopefully there will be some already command exist there. So this is the command, okay, for the design vision. We try out to best to wrap up this CDC solutions as quickly as possible, because this already get lengthy in scenario from the solution 1, 2, 3, 4. Okay, so at the last we get the setup violations slack as a positive, so it will work for the 100 mega. Also the path for the min path is means hold violations, it also meeting the requirement. We get the reports, all reports. This is our area report with 90 nanometers. So okay, power report, timing report for the maximum path 1 for the setup and hold violations that we already seen there. So from that we can say we can still have some space for the more than 100 mega. Okay, now quickly check the, first we go for the GUI, what it look like in schematic ways. We quickly visualize this symbol for the FIFO and quickly the schematic. Okay, so under this FIFO, main FIFO, it is implemented by the flip-flops. So obviously there will be some timing constants limitation here, because memory is implemented using the flip-flops. Okay, so anyway, if you have vendor based any model, you can have that plug down there, and you can define the vendor RAM. Okay, so move back to the just view the that gate net list, DC 90 nanometer, then FIFO 90.v. This is our gate net list, might be little bit large. Okay, so anyway, we move back to the for the simulation VCS. First we check the Makefile. So under this Makefile I add two more things, synth 90 and synth 45. because I have two libraries, so the mode will be RTL for the same synth 90 for the 90 nanometer, synth 45. To use the 45, we have to go to the design vision, make the synthesis using the 45 nanometer using critical file alternate for the library section. Okay, so while giving the command I refer the synth, but in this code we can use the synth 90. Okay, for the reference I just scroll down little bit to know what I write for this. You can pause and you can check. Okay, there is no much to explain here because this is the same critical file that I refer in the EDA tool tutorial or earlier simulation setups, so you can refer that also. So to make the post synthesis simulation, we just comment the file list for the FIFO, that is our top. So I just comment it so that it will refer the synthesis get netlist in spite of this RTL get netlist. So the command is make top equals to name of the module, which is our test bench module, and the mode, that is our synth 90. Okay, I hope there is a command also there. Okay, this is the command make top name is our test bench module name, this is a mode synth 90, just enter it. So there will be the pop-up menu for the DVE. From that we can select the signals and run the simulation. We need to check confirm that it is for the get netlist. Yes, it is for the get netlist. So I just select all, Control A, Control 4. It will pop up a new window for the waveform. Okay, I just align with the window. Just hit F5 for the zoom fit. Press F. Okay. So this is our data, right? Read data, then R data. R data 2 is a double flop with the R data, so there is no need for the R data 2 here. So the FIFO full, once the 16 data get completed into the FIFO, okay, RMT is there initially. Once it will gradually written by some host signals. This is a write clock, read clock, increment, write increment, read increment. These are the resets. So at last I think we get the empty also. So might the signal is not completely there because I stop at the final one. Okay, I think this, yes, I final finish at 100. You can extend this to have that look. So under the code td under FIFO, I just increment that value. Let's say 4 5, let's say 4 5. Let's try again. Quickly just wrap up these things, and please subscribe my channel. So I just forget to mention you only these things, but I think I have to mention it. Please subscribe my channel, like, comment and share also. so it will motivate me. Anyway, Control A, Control 4, F5, hit fit zoom. So still I think we not get that empty signal here. Okay, because we have to still read the more data. Okay, I hope that you got the point there. Okay, so after the 77 it will goes for the empty. Now we are at the 3D. Okay, so anyway, I hope you got the points. Thanks. Okay, bye.